Hi everyone. In this video you are going to learn about FPGA design flow. FPGA design flow we have seen in the beginning of this VLSI subject. I have explained VLSI design flow where we have seen how to write the program based on the design specification and what are the different programming languages we have to write the hardware description language, and later we have simulated it. That's it. Just till the simulation part we have seen in the case of VLSI design flow. But whereas in the case of FPGA design flow, we are going to write the program first, later simulation. After that, we are going to synthesize it. After synthesis, we are generating the netlist of that bit stream and thereby dumping onto the FPGA board. Okay, this all process will come under this FPGA design flow. I will explain one by one. So first FPGA stands for field programmable gate array. Field programmable gate array. FPGA stands for field programmable gate array. That means it is having number of logical elements. It consists of group of logic elements known as gate array. All these logic elements are used to implement any type of logic function. It is a customized one. Okay, FPGA can be used to implement any type of logic function that we are looking for. Okay, so that we can create any type of logic function and we can manually or physically verify its operation based on our input switches and output LEDs. That is the FPGA importance. Now, FPGA design flow gives the information about the creation of bit stream and dumping onto FPGA board. Okay, in this design flow we are going to study about the creation of a bit stream, how the bit stream is going to be created, and later we are going to see the dumping onto the FPGA board. So this dumping onto the FPGA board, once the dumping is completed, then we can verify our physical operation of the logical circuit whatever we require. Okay, so let us move on to the FPGA design flow. See, this is the FPGA design flow diagram where the first step includes design specification. Design specification is nothing but we are going to consider what is the requirement of the present situation. So in the design specification, we consider what the design says. That means we will go for the requirement of present situation. Suppose at this in this moment I want to create a multiplexer, or I want to create an AND gate, I want to create OR gate. So depending upon the present situation, which type of logic function you are looking for, that we will consider in the design specification. So design specification tells how and what type of design we need to consider. That we will see in the design specification. And the second one is behavioral description. Behavioral description is nothing but we are going to write the hardware description language for this. We are going to write the hardware description language for this type of considered logic circuit. So behavioral description. In this behavioral description, we are writing the behavior of hardware in a programming language. A programming language. So what are the different programming languages we have? What are the different programming languages we have? For our VLSI, there are two types of programming languages we have. One is VHDL, another one is Verilog. VHDL and Verilog. These Verilog HDL. These are the two programming languages that we can write our hardware description language. So VHDL again specifies very high speed integrated circuit hardware description language. VHDL stands for very high speed integrated circuit hardware description language. This V itself specifies very high speed integrated circuit, and HDL we know hardware description language. So in these are the two different languages we are going to write our behavior of the hardware. Okay, suppose if you are saying AND gate, a 2-input AND gate. 2-input AND gate, if you consider how you are going to specify that in terms of program, we will consider A and B as input ports and Y as output port. Then simply Y is equal to A and B. This is the way to write the VHDL code for 2-input AND gate with output Y and inputs A and B. Okay, suppose if it is a VHDL code, that is the way. In VHDL, the input and output ports are separated, and behavior of the code is written in architecture. In VHDL, input terminals and output terminals are in-out. We can say input, output or in-out are specified in entity. Okay, so entity is a place where ports are specified. Ports are nothing but input port, output port and in-out port. And behavior, nothing but description. Behavior we can say or data flow. See here in VHDL there are three types of programming written styles are there: behavioral description, data flow description and structural description. So that what type of model we consider, that will be written in terms of architecture. So behavior of hardware will be in architecture. Okay, so there are three different styles are there: structural model, behavioral model and data flow model. Okay, the behavior can be written in three styles. One is structural model, second one behavioral model, third one data flow model. Okay, in structural model of VHDL, we are writing based on the structure. Suppose if you are having a full adder, in that full adder, how many AND gates are there, how many OR gates are there, how many XOR gates are there, that we will consider, and we will write the individual programs first for all these gates. Later we will interconnect all these in a main program. This is what the structural program says. And coming to behavioral model, in the behavioral model we are writing the code based on the truth table. That means what happens when a equal to 0, b equal to 0, c equal to 0. Likewise we will write each and every step. And coming to data flow, in data flow we are going to write the program based on the expression. Based on the expression. This is for expression. Okay, in behavioral modeling, truth table. Based on truth table we are writing. In structural model based on structure, internal architecture. Okay, so these are the three different styles we are going to write for VHDL. Similar case with respect of Verilog also. Verilog HDL, suppose if you want to write the same AND operation in Verilog, in Verilog, y simply is equal to a and b. This is the ampersand, two ampersands operation which specifies AND operation in the case of Verilog. Okay, in Verilog we don't have any entity architecture. We are having a module. Here we don't have entity and architecture. We have module. We have a module. Just simply module is there. Inputs, outputs are directly specified, and then we are going to write the logic operation without including any port, any entity and architecture. This is Verilog. We can say it is a simplified version of the VHDL. In this way, we are going to write the structure of this behavior of this hardware description, and the next step is RTL description, where this hardware description language is converted into a register transfer level description. Okay, we can say this third step is nothing but RTL description, where the program will be converted into RTL. RTL stands for register transfer level. So here what happens, the completed program will be just simulated, and then we will be having the register transfer level. All these the description whatever we have written so far will be converted into registers, and lookup tables are created and they are interconnected based on the written program. And the next step is functional verification and testing. This functional verification and testing is nothing but simulation. Okay, so fourth step, functional verification and testing. How functional verification can be done and testing will be done? So once the program is written, then we will verify the errors. Okay, if any error is there, again we will modify. Okay, no errors is there, then we are passing the inputs and verifying the output. That is called testing. Okay, here errors are verified once it is correct. Next step is to verify the input and output. Okay, so suppose y is equal to a and b I have written, then I am taking a condition like A is equal to 0 and B is equal to 1. For this situation, so whether Y gives the same output, whatever we originally required, we are giving. So if we are having this type of output, then our logic circuit is tested and it is okay. If it does not give this particular required output, then again we go back to the program and we will see the operation where we have done some error or mistake. Okay, so once the testing is also okay, testing after that if it is okay, then we are moving to the logic synthesis and technology mapping. See, till this functional verification and testing you have seen in the case of VLSI design flow. Our next task is to create the synthesized file netlist bit stream and then dumping onto this FPGA board. So logic synthesis and technology mapping. In this logic synthesis and technology mapping, circuit is synthesized. Logic synthesis and technology mapping. So what do you mean by logic synthesis and technology mapping? Logic synthesis, once the simulation is okay, and that means input output waveforms, we have got the required outputs, then we are synthesizing the circuit. We will synthesize the logic circuit. In this, we are going to first synthesize the logic circuit. After synthesis, the port mapping should be done. That means technology mapping should be done. See, what type of technology mapping should be done? If you take FPGA, there are several families in FPGA. Okay, FPGA consists of like RTX family, Altera, Vertex family. Likewise, we are having several number of families. Okay, RTX, Altera, Vertex. We have so many families in the case of FPGA. In RTX also we are having several families. In Altera also we are having several families. In Vertex also we are having several families. All these are families I will explain in future classes. So if you take a particular RTX family, what type of board you are selecting? What type of FPGA board you have selected, that you should specify in the technology mapping, because the technology of the input outputs of this particular program must be mapped to the input outputs of the board what you are taking. Okay, that should be done. Without knowing the board, we cannot compare with the FPGA board and the Vivado environment or Vivado and Xilinx environment. Okay, so definitely mapping should be done with the board you have in your hand and the program you are writing. Okay, so that is called technology mapping. In technology mapping, once in technology mapping, particular board is going to select, and then IO mapping should be done. Okay, in technology mapping, IO mapping should be done and port and a particular board is going to be selected. Okay, so next, what is the next step? Sixth one. Sixth one is technology netlist. Technology netlist. Okay, so once the technology mapping, IO mapping is done, then netlist will be generated. Netlist corresponding to selected IO mapping will be created. Okay, so this netlist purpose is to create the bit stream which is going to dump onto the FPGA. Okay, next placement and routing. We have several number of logical elements in the FPGA. I told you it's an array. Okay, what type of which logic element we need to select, and if we are selecting more than one logic element, how they are interconnected. Okay, that will be done in the case of placement and routing. Required number of logic elements are selected and interconnected. This is placement and routing. And then bit stream, very important file, bit stream. So bit stream is a file where the entire program and the entire logic function what we are completely going to dump onto the FPGA, that will be created in the form of bits. Okay, it is a file supported by FPGA board to dump. Okay, so it is the main important file that is going to be supported by the FPGA board, which you are going to dump on it. Okay, this bit stream consists of your required file. So whatever the input outputs and mapping you have done, logic circuit you have written, so everything will be written in terms of bit file. So that bit stream file, it is saved with dot bit. It is saved with extension of dot bit. Okay, and the last one is dumping. So here a cable is connected between system where you have done all these things and FPGA board Next, after dumping, it shows done on board. Okay, so once if you find this done light corresponding on this FPGA board, then we are saying that it is completely done. Then we can verify the operation of the required logic function. So in this way, the FPGA dumping is going to be done for the corresponding program what we are writing. Okay, this is 6th step, 7th, 8th and 9th. Okay, so this is the operation of FPGA design flow and how we are writing a program and what are the different styles we have, how to verify its operation, later synthesis and technology mapping. Once the netlist is generated, next task is to placement and routing, and then bit stream is generated. Later we are going to dump this. Thank you.